What's up, everybody? Today the focus is on being able to raise a complex number to a power. You can do this in its rectangular form, but sometimes that can be pretty tedious and long to do, especially when you're working with large powers. If you have the number in its polar form, then you can apply what's referred to as de Moivre's theorem to raise it to a certain power. So here, notice the theorem. If I'm trying to take this complex number of z and raise it to the power of n, all I need to do is take its modulus r, raise it to the power of n, and take its angle theta, multiply it by the value of n. Okay? And understand that this is really just an extension of how we find the product between two polar complex numbers. If we go back and we look here at what's circled in blue, so whenever I multiply two complex numbers together, I'm just multiplying their r values, their moduli together, and I'm adding their angle measures, right? Well, you got to think raising to a power is just repeated multiplication, right? So if I'm taking z and I'm raising it to the power of n, it just means I'm multiplying it by itself n times. Therefore, r would be multiplied n times. Therefore, r to the power of n. And then theta would be added n times, which is n times theta. Okay? So let's apply the theorem on this example in front of us. We have the complex numbers already in its polar form, 2 times the quantity cosine 20 degrees plus I sine of 20 degrees, and we'd like to cube it. Okay? So applying the theorem, I'll end up with 2 cubed multiplied by cosine of 20 degrees times 3 plus I times the sine of 20 degrees times 3. That's going to lead me to 8 multiplied by cosine of 60 degrees plus I times the sine of 60 degrees. So that would be your simplified number in its polar form. Notice the directions, however, they want us to write our answer in standard form. Okay? So that means I'm going to have to find both cosine and sine of 60. Let's visualize that. Okay, so cosine there is 1/2. Sine there is radical 3 over 2. Then you can distribute your 8. And you'll end up with 4 plus. Now when I multiply 8 times I times radical 3 over 2, that's going to become I times 4 radical 3. Best way to write that, let's go 4I radical 3. Okay. Taking this approach using the polar form and de Moivre's theorem is actually a lot quicker, a lot more efficient than if you were to have tried to use the rectangular form of this polar number and multiply it by itself 3 times. Okay. All right, one more example. Here, we're trying to take the the rectangular number radical 2 plus I radical 2 and raise that to the 6th power. Okay. You are more than welcome to try and multiply that by itself 6 times in the rectangular form. I think that's going to be pretty tedious and time consuming to do. Okay. If I can get the polar form associated with radical 2 plus I radical 2, then I can apply de Moivre's theorem. It's going to be a little quicker. Okay. So let's begin. Let's just visualize this in the complex plane. Okay, so it's going to be in quadrant 1. That's radical 2. That's radical 2. Since those are the same length, we know that theta is 45 degrees here. And then the r value is just going to be 2. Okay, if you're not sure on that, just use Pythagorean theorem. 2 plus 2. Of course, r is going to equal the square root of 4 or 2. Okay. So really what I'm working with here is 2 times cosine of 45 degrees plus I times the sine of 45 degrees. And I now want to raise that to the 6th power. So applying de Moivre's theorem, I'll take the modulus of 2, raise that to the 6th power, and I will take my angle measure of 45 degrees, and I will multiply that by 6. Okay, so 2 to the 6th power is 64. And then 45 times 6 is 270. All right, so there would be the polar form of your resulting value. But notice, once again, directions are asking for the standard form. So I'm going to need to distribute here. Before I do that, though, let's just find, let me back up. Let's find cosine of 270 and sine of 270. So that just places you down here on the unit circle at the point of 0, -1, right? So cosine for that is just 0. And then sine for that is -1. Okay. So we distribute the 64 now, and we'll end up with 0 minus 64i, or simply -64i. And there you have it.